Right, good afternoon. My name's Jon Diprose. I work for Rob, and we are, as Rob said, looking into getting Lustre systems. And one of the things I've particularly been asked to look at is Kerberos integration. I'll skip over this one because Rob's already done that, except to say I feel a little bit of a fraud standing up here because I am not, in fact, a Lustre user. I want to be a Lustre user, but mostly, historically, we've been grid scaler on DDN-Kit. So why Lustre? It's particularly the multi-tenancy, and I have to say a big thank you to all of the work that's come out of the Sanger on, that they've published on secure Lustre. It is that in particular that makes us think that Lustre is going to be able to deliver for us in the future. Why Kerberos? The Kerberos has a couple of interesting security features that we might have reason to rely on. One of them is the strong authentication, KERB5N, and the other one we're looking at is the full encryption in flight, KERB5P. We get data transfer agreements that mistakenly say all data must be encrypted in flight and forget to say we mean between institutions and not inside an institution. And that sort of thing starts to get interesting. But as we move into a cloud world, actually we don't own the network anymore, and perhaps we do need to be doing encryption in flight. And finally, we're already using Kerberos, so our identity management platform is FreeIPA. That is the upstream of Red Hat's identity management platform. Kerberos is part of that. When our users log in, they get a Kerberos ticket already. They don't use it, but they get one. A quick introduction to Kerberos. There are four kind of key concepts. There's a key distribution center, which has two primary roles, an authentication server and a ticket grant server. The keys in Kerberos are moved around the place as something called tickets, and there are two main types of ticket. There's a ticket granting ticket, which, as the name suggests, is a ticket that allows you to get other tickets, and there's a service ticket. And a service ticket allows you to access a specific service. It's particular for a single service. Those tickets have a finite lifetime, and they are stored in something called a credential cache, so that they can be retrieved and reused during their lifetime. Kerberos principals are anything that can hold a ticket, essentially, and the main sorts of principal are users, hosts, and services. The final concept I'm not really going to touch on today is key tabs. Users might be expected to authenticate interactively. The hosts and services can't really authenticate interactively, and the key tab is an encrypted password store to allow them to do a non-interactive authentication. So if we have a user who wants to use a Kerberos-enabled service, this is pretty much how it goes. They log in, they authenticate themselves to the KDC, to the authentication server, and if their authentication checks out, then they're given a ticket-granting ticket, and that ticket-granting ticket gets stuffed into the credential cache for later use. When they want to use a Kerberos-enabled service, the first thing they do is get that ticket-granting ticket back out of the credential cache, give it to the ticket grant server and say, I'd like to use this service, please. And if the ticket-granting ticket is still valid, they'll get a service ticket that's good for that specific service. When they're actually using the service, again, they get their service ticket out of the credential cache, they give it to the service, and if the service ticket is valid, then they'll get a response from the server. Now, Kerberos obviously is the three-headed hound that guarded the gates of the underworld. I had three major problems when I was trying to get this going, so I'm going to borrow that analogy. And my first problem, my first head, was the credential cache, which is where the tickets are persisted. Red Hat 6 used a mechanism called file, which basically meant stick it in /temp. Red Hat 7 introduced a new mechanism called keyring, where the ticket gets put into the kernel key store, which was great for a while, but then containers started to get really popular, and one of the things with containers is they're all sharing the same kernel, and so that started to break as the users in the containers weren't all the same. Might have the same UID, but they weren't actually the same user. And so Red Hat 8 uses something else called a Kerberos credential manager. My clients that I was using for testing were all Red Hat 7, and I was getting nothing out of Lustre at all. And eventually it became clear that Lustre uses file. That fortunately is a rather straightforward change to the Kerberos config, just a one-line change, but that's not mentioned in the documentation. So that was head number 1. Head number 2 is name resolution, and this I think is an area where Lustre features have marched on past the documentation. So a Kerberos principal has an identifier of the form, or a service principal has an identifier of the form service/hostname.domain name at realm. Now the service bit is defined by Lustre. There are 3 or 4 service names parts of the service name that you have to register for Lustre. The realm name is defined by your Kerberos instance. The bit in the middle, the hostname.domain name, is covered by a bit of documentation which says that if you can do name resolutions, so IP over IP and Ethernet, the names used in the principals must be the ones that resolve to the IP addresses used by Lustre NIDs, which is great if you've got one IP address on your server. We're using multi-rail, so we've got multiple IP addresses facing our clients, and we also have management addresses on our management IPs on our server, so we have IPs that aren't facing our clients. We'd get odd things to happen. Lustre would look like it was starting, and then it would stop fairly quickly. And we cycled around a variety of different configurations before we settled on the host name must be associated with an IP address of one of the client-facing NICs. And all of the client-facing NICs, the IP address must resolve to that same host name, because otherwise it just can't build the right service principal. Similarly, on the client side, all server-facing IPs must resolve to the host name of the client. And then you do the Lustre mount using IPs instead of host names. I haven't actually used Lustre enough to know whether it's unusual to do the mount with IPs instead of host names, because that's all I've known, essentially. To me, that DNS config feels a bit dirty. I don't like starting off with an IP address, resolving a host name, using the host name to resolve an IP address, and not getting the answer I started with. But there's plenty of that out there in the big wide world, so I'll just have to get over that one. The third one is the one that had me, the third head is the one that had me stumped for ages. Key quota exhaustion, which I'd never heard of. I didn't even know there was such a thing. So in Lustre, the Kerberos service ticket isn't the thing that's used to actually protect the data transfers. The service ticket is used to construct a GSS context. That's exactly the same way that Kerberos NFS works, which is unsurprising because there's a shared history in the code. I believe the Lustre code came from NFS utils 1.2 or 1.4. The context is represented by a key of type LGSS. That key type is defined by one of the Lustre kernel modules, and that gets put into the kernel key store. Now, it turns out the kernel key store has a per user quota, both on number of keys and on the amount of space those keys can take up. The defaults are 250 keys and 20K worth of space. When the keys are constructed by Lustre, they're attached to something called a session keyring. A session keyring is a special sort of kernel key that groups other kernel keys. That session keyring is created by a PAM module when you log in. So one of the modules in the PAM stack for an SSH login is keyinit, and it creates that session keyring. Every time you do a new SSH login, you'll get a new session keyring. And because the LGSS keys are attached to the current session keyring, that means that for each of your logins, you'll get LGSS keys that are specific to that login. Now, you can clear out the LGSS keys by calling lfs flush ctx, and that then removes all of the LGSS keys. When you log out of your SSH session, the session keyring is destroyed. If you haven't flushed your LGSS keys before you log out, they become orphaned. They persist, they count against your quota, and the access control in that key store is really good. You can't delete them. You can see that they're there, but you can't delete them. The only way to get rid of them is to unmount the file system, and that's obviously pretty intrusive. I was using IOR for my benchmarking, which is OpenMPI. There's no way I can get an LFS flush CTX called at the end of each IOR rank, and so it turned out I was leaking keys at a rate of essentially 4 an MPI rank. So my run would go through 30 or 40 cycles, and then it would fail, and it would fail pretty much consistently at the same time. Simple fix, when we'd figured out what was going on, you can bump the quota, and that's under the control of sysctl. Bumped it high enough so that my IOR runs would complete, but that is obviously not a long-term fix if you're continuing to leak constantly. A bit of poking around. Subsequently, we're able to find the code that actually creates and destroys the session keyring in the PAM module PAM key init, and did some adaptation of the code so that that calls LFS flush CTX as part of the PAM session close down, and now my keys all get flushed. That code I've sent on via Vic to WAM Cloud, so that will hopefully at least make it into some documentation. Engaging that new PAM module is a one-liner change in some PAM config. Log out, log back in, and I can run my IOR runs at last. Okay, so I have 46 2-core VMs, 92 cores in total. These are graphs of a scan across the increasing node count for IOR, 2 meg reads, 2 meg block size on a 1 gig transfer size. The dogleg on the read is the transition between 1 process per VM to 2 processes per VM. And essentially, the good news for us is that KRB5N is essentially painless. The bad news for us is KRB5P is horrible, looking at cutting down to about 40%, which is about the same numbers that Sebastian Bisson was reporting in 2015. Looking at the metadata tests, you can see that there's a slight hit on the stat as you turn on KRB5N, and it drops down significantly by the time you got down to KRB5P. Interestingly, on file creation, the largest proportional hit is simply on engaging KRB5N. So, is KRB5P going to be the answer for us? No, it's not. Client-side encryption has come along in the meantime, between us starting to look at Kerberos or our awareness of it. We became aware of it after starting to look at Kerberos. KRB5P, the performance sucks. The real problem actually for us is it's on or it's off for everybody. So everybody's going to have to face the pain. Whereas the client-side encryption, that's a per directory config. We can have that only on for the people who need it and off for the people who don't. It has in principle no impact on the server at all. But I've been unable to do any testing on that because the requirement is a client. It's a client-side requirement. OS greater than Red Hat 8.1. My VMs are all 7.9, so that's on my work list for when I get home. We're still likely to want to have KRB5N switched on though, so that is that's still something to look at. But as I say, not expecting that to take a big performance hit. One of the things that came up in discussion with DDN is that actually with 2.14 you encrypt the client-side encrypts the data. With 2.15 you encrypt the file name. Metadata, file size, modification date is still plain text. I don't think that would be a problem for us, but if it would be a problem for you, it is possible to turn KRB5P on for metadata and leave KRB5 on for the bulk transfers. And this is just to show that actually if you do that, the reads, no change. The writes take a hit, which I can't explain. It drops down to about the same level as the checksumming Kerberos level, but I don't think those two are related. And just to show that it's definitely engaged, you get KRB5P metadata performance on both the stat and the file creation, so it definitely looks like it is actually doing what it says it does. That's all that I wanted to say today. I'd particularly like to thank Adam for giving me all the VMs for testing, and Vic and Sebastian for helping actually getting some numbers out to give you today at all. And thank you very much for listening.